Kia ora, everybody. Dr. Harves here, going through a couple of exam papers from last year, 2022's papers, and giving some little also some hits and tips along the way. So if you want to get involved and have any questions as we go through the questions, be sure to use the YouTube chat. So hopefully you can all hear me. I'm trying out a new microphone today. Anyway, without further ado, let's begin the lesson. So let's share our screen. So we'll start off with the mechanics paper. There we go. Start sharing the screen. And we'll work our way through the mechanics paper first, then end off with some tips and hints, and then we'll work on to the electrical systems paper. Oh, that's the wrong one. Stop sharing that one. It's that one we want to share. So present, share screen, getting used to this new platform. So I think that's the one. Yep, share mechanical systems. Right, there we go. So it should be up and running now. So level 3 physics, 2022, 91524, demonstrate an understanding of mechanical systems. Okay. Copyright, you don't get another wonderful picture of children playing in a roundabout. But anyway, question 1, begin with that, rotational motion at the playground. Okay, so in this case, Riley pushes the roundabout and gets it spinning at a constant angular speed. So the way I always think about questions is I break them down and what they're actually asking. So they're asking for an angular speed, and it makes one revolution in 1.23 seconds. Okay, so what we have to do is show that the angular velocity of the roundabout is 5.11 radians per second. So we look at our equation sheet and see, well, we've got some sort of time here, and it's about 1 revolution. So the equation I would use is omega equals 2 pi over t. Okay, so that's 2 pi. Now time period from the question is 1.23 seconds. Okay, and that should equal 5.11 radians per second. Okay, and that's your achieved point there because you've just shown it. So that should be quite straightforward. Okay, so then we move along. And again, always breaking down the questions. So Riley stops pushing. Remember now we have an omega of 5.11. So it stops pushing and there's a 30 seconds. So there's a time component in the question potentially. So it takes 2.04 seconds to make 1 revolution. And the roundabout has an inertia of 57.6 kilograms per meter second. The question asks 2 things. Determine the average angular deceleration of the roundabout as it slows, and then calculate the average frictional torque acting on the roundabout as it slows. So in terms of average angular acceleration, well, let's just work through that. So we know that the final angular velocity is going to be taking into account 2.04 seconds. So again, it's going to be 2 pi over 2.04, which gives us a final angular velocity of 3.08 meters per second. Okay, so we've got a final angular velocity. We've got an initial angular velocity. So we can actually work out the angular acceleration because we know that the angular acceleration is going to be the change in angular velocity over the time period. And from our previous question, we have an initial of 5.11. Okay, so it's going to be 3.08 minus 5.11 divided by the time that takes. And we're told in the question, if we go move it up slightly, that it takes 30 seconds to slow down. So it's divided by 30.0, which if you plug in the numbers will be 0.068 roughly. Okay, radians per second. Okay, and that's going to be where you're going to get your merit from, calculating the angular acceleration. Okay. Yeah. And then it says calculate the average frictional torque acting on the roundabout as it slows. So we'll kind of do it in this part here because I've had a room. Okay, so torque, if you look at your equation sheet, which you should have in front of you as we go through this, is I alpha, and we've just worked out alpha here. And in the question, you've given the rotational inertia anyway, 57.6. Okay, so it's going to be equal to 57.6 times minus 0.68, which equals, in my wonderful doctor's style writing, 3.9 Newton meters. Okay, and that's where you're going to get your merit, because that's more than one calculation. Okay, so that's how you would work that out. So always try and break down the questions into components and see what equations fit, and that way you can move towards merits and excellence. Okay, so this is going to be the X component now, discussion around explaining, because explaining questions are always where the excellence points lie. Okay, so using physics principles, what the friends can do to make the roundabout speed up while staying on the platform, and you need to exclude all influences external to the platform. Okay, so in terms of basically what you're looking at is you want to reduce the distance that they're going to the turntable there. You want to reduce the distance there actually away from the center or towards the center. Okay, so that means, because remember, the rotational inertia will equal the sum of the mr squared. So you can always use equations, and it explains questions, and that's where you can basically save time if you're in a rush, because equations in physics are just ways to describe physical phenomena. Okay, so basically they can decrease the initial inertia or rotational inertia, because they're going to reduce the radius. Okay, they're moving closer towards the center of mass. Okay, and there's no external torques, because the question explicitly says that. That means that L is conserved. Okay, so what is L? It is the angular momentum. Okay, that's why it is conserved. Okay, and I'm running out of room again. Must do a better job at that. So since L equals I omega, okay, since the I is decreased, as we've seen here, therefore omega must increase. Okay, so that's a very much, you can write that out in words, but it's just as effective to use equations to do exactly the same job, okay, to explain it to the examiner that you understand the physics. Okay, so in order to get a chi for that point, you're just mentioning that the friends have to move to the center of the turntable, or the round, whatever it's called. What is it called? The platform, basically. That will get you, and therefore the I will decrease. Okay, that will give you the chi point, and then a justification linking it to center of mass is where you're going to get your merit, and then a complete answer has to then incorporate the idea of conservation of angular momentum, which is this part here. Okay, then it's your excellence point there. Okay, so now Matilda wants to run and jump onto the initial stationary roundabout, holding onto poles at A or B to make it spin as fast as possible. She tries different jumps onto the roundabout, so you can see the different positions there, assuming that she always jumps at the same speed. Okay, so just maybe underline when you're answering the question. Explain the jump, A or B, that will make the roundabout go fast. K value, so it can be 2 for different shapes. What's the E in? It's not E, I think. Oh, sorry, yeah, this. All right, it's not actually an E. It's my very poor writing because I'm a doctor. Okay, it's actually, let's put this down. It's a sigma. Okay, sigma is the sum. Okay, it's the sum of all the masses and radius. That's actually what the inertia actually represents. It's a sum symbol from the Greek, capital. Okay, So it's the sum, adding them all up, not an E. Okay. So assuming, so there we go. So assuming she will jump to the C, explain which jump A or B will actually make the roundabout go around faster. Oh, what's that? Other side. Okay, there are we. Just make sure I got that correct. Okay, so the answer is A, but that probably isn't going to get you a mark. Okay, yeah, sigma. Okay, thanks for that, yeah. But yes, it's a sigma signal, sum of. Right, so A, okay, so the reason why you have to have basically an increase in torque or an increase in angular momentum, okay? How does that come about? Well, you're using the equation torque equals FR, which you should be able to find on your equation sheet, okay? So assuming the applied force is the same, the perpendicular distance to the rotational axis is larger at A, so the R increases and therefore T increases. Okay, so you're looking at this here. So forces are pretty much the same, but as you increase the radius, then the torque is also going to increase. Okay. Yep. And that occurs if you look at the model. Okay, it occurs at point A. Okay, it's furthest away from the center, the radius. Okay, so it's a larger radius. Increase in torque. Okay, we also know that L equals mvr. Okay, about the velocity there. Okay. So again, that occurs. So when velocity increases, and also when R increases, the angular momentum will also increase. The last point, yeah, so basically the last point is at point A, it's the greatest radius from the center of mass compared to point B. So therefore, as R increases the radius, the torque increases, which will increase the speed because the angular momentum will equal mass times volume times R. So again, R is increased, velocity increases, the angular momentum increases. So it's quite useful just to break down, put down the equations into the question, and then work from the equations. Okay, so what's the rest of the question ask? Assuming A or B will make the roundabout go faster. Yeah, that's pretty much it. Okay, in terms of jumping off, so slipping off won't affect the speed because she doesn't exert the torque when she's slipping off. Okay, or even when she slips, she does not remove angular momentum from the roundabout. She only removes her own angular momentum. Okay, so in that way, the angular momentum of the system is going to be the angular momentum of Matilda plus the roundabout. Okay, so the roundabout's momentum doesn't change. Okay, because it's being conserved. That's conservation. And that's where you get your excellence from. So you could write that out or use equations. Okay. So Matilda subsequently lets go of the pole and slips off the roundabout. Discuss, that was actually what we've just gone through. Discuss the possible effects on the speed of the roundabout and assume there is negligible friction between Matilda and the roundabout. So that's, again, what I've just actually discussed preemptively in the first part is when she slips, she does not remove angular momentum from the roundabout. She only removes her angular momentum from the system. Okay, which you see in that equation at the bottom. Okay, so that means that the roundabout doesn't change its angular velocity even though she slipped off. And in the case of slipping off, again, she does not exert a torque, so she's not changing the speed because of that. Yeah, so no external torque means it doesn't increase the speed either. Okay, so no effect basically when she slips. There's no effect on the speed of the roundabout when she slips off. And that was part B or dii. Okay, so that's the first question around angular momentum and angular velocity. So you have to basically have an understanding of conservation of angular momentum going into the exam, because that definitely will be assessed in some sort of context, and also looking at torque as well. So get familiar with those equations. Yeah, because the roundabout is going, the radius, the angular momentum of the roundabout increases in relation to the system. Yeah, it's a sum. Because she's not removing angular momentum from the roundabout. She's only removing her own angular momentum from the system. Right, so question 2, collisions in space. So again, these kind of questions, momentum in 2 dimensions, will definitely be asked. Okay, that's for sure. Because, yeah, it's just key to the level 3 curriculum. So collision in space, comets and asteroids are loosely formed objects that can easily be broken up, especially, yeah, exactly. Harvey's my dad, yeah. So it's actually part DI. That's what that's discussing. So comets and asteroids are loosely formed objects that can easily be broken up, especially when they collide. So we've got a scenario. So you have a mass, okay, with a velocity, and it collides with a second mass, okay, M1, M2, and a V1. Okay, and it's also in the diagram there. Okay, so calculate the distance of the center of mass of the system. Okay, so center of mass equation straight from your formula sheet. Okay, so we'll just plug it in. It's the XCOM one. Okay, XCOM equals M1 X1 plus M2 X2 divided by M1 plus M2. So if you plug in the numbers, which we're going to do, 100 times 4,000. This is painful, but there we go. Plus 300 times 0. That's quite lucky. Divided by 100 plus 300. So if you get your calculator out and do the calculation, then you get a center of mass of 1,000 meters. And that gets you an achieved. Simple. Right, so it says calculate the gravitational force between the 2 objects when the center of mass is 10 meters apart. So you've got a gravitational force idea, you've got a distance, assume the velocities are constant. Okay, so again, going to your wonderful formula sheet, we've got a gravitational force. So the only gravitational force equation I think you've got is the big G, big M, little m over r squared. Oh boy, let's do this calculation as well. Okay. Yep, so we just plug in the numbers again. So the universal constant, which will be given in the exam, 6.767 times 10 to the negative 11, times the big mass, which is 100 times 300 divided by 100 plus 300. Actually, it's not really the big mass, is it? Because it doesn't really make a difference for this particular example what mass you use. Yeah. But it's interchangeable anyway. 100 times 300 and 300 times 100 is the same number anyway. Divided by 400. So if you plug in the numbers, you should get, what have I done? Oops, I've got the wrong equation. Let's do that again. That doesn't make any sense. There we go. Okay, so where was it? So 6.67 times 10 to the negative 11 Oh, was it times 100 times... oh, yeah, I don't know what I did wrong. 100 times 300. And then you divide that by r squared, which is 10 squared. There we go. That's what I did wrong. Okay, and that should give you a number of 2 times 10 to the negative 8 newtons. Okay, and that's obviously going to be your achieve point. And then we move on to hence find the acceleration. This is your merit point of 1 times 10 to the 2 kilograms object in this separation to determine whether the assumption of the velocity is a constant before the collision is valid. Okay, how am I do this? Okay, so the acceleration, so this is going to be your force. Okay, so force equals ma. Rearrange it to get the acceleration. So it'll just be 2 times 10 to the negative 8 divided by the mass, and 100. And that will equal 2 times 10 to the negative 10. Okay, just simply Newton's law. I need to... Okay, and that's going to give you your acceleration. And the assumption that the velocity is constant is valid because the rate of acceleration is very small. Okay, it's times 10 to the negative 10. Okay, so it's very small. So we're pretty happy with that assumption. Okay, so that should give you a merit. Or actually, you could argue, I guess, you could say, well, actually, it's not valid because there is actually an acceleration, even though it's a very small one. So you could either argue it's valid because it's negligible, or you could argue it isn't valid because there is an acceleration. I've just calculated it. It's 2 times 10 to the negative 10 meters per second per second. So actually, depending on the evidence that you use, you could get a merit either way. The glory of science. Okay, so now the objects collide with no external forces. Okay, what will be the better answer? Well, actually, both are correct. Yeah, they both give you merit. Yeah, because you're arguing a case with evidence, and that's what science is all about. Yeah, so both would be valid answers to get merit. So the objects collide with no external forces and form 2 rocks, A and B, okay, and they have a mass, each with a mass. Okay, so we've got 2 masses. They move away each other in a direction of 20 degrees. Okay, so we've got 20 degrees. So here's our 2D momentum question. Okay, show the size of the momentum of rock A and B are the same, even though they are in different directions, and they've even put a nice little box in there. Okay, show the size. I guess I could do an algebraic proof. So since the initial total momentum is horizontal, so we go. So we've got there. So there's 2 ways you could do it. You could either use a triangle, or you could do it using algebraic proof. Okay, so let's do it with the algebraic proof. Okay, so let's go. So the momentum of A, what's it, hot? Equals cos 20. Oops, let's do that. Let's do a better job. Divided by cos of 20 equals the momentum of B over the cos of 20. So therefore, PA equals PB. Yeah, so you could do that, or justify using an isosceles triangle with vector addition triangle referred to diagrams in T. Yeah, so there's 2 ways you could do it. You could either using it that way, or you could create a vector diagram, which will solve it that way. Okay. So state any of the following reasonings. I guess also you have to say that the total momentum is the same before and after. So that's your conservation of momentum. Okay. Well, what else could you say? That the mass and angles are the same. Okay, so you can see from the question that the angles are the same as well. They're 20 degrees. And angles are the same. And what else could you mention? Momentum in the y direction, as you can see from the diagram originally, is going to be 0 initially. So the momentum in the y direction, the final, will also be 0. Okay. So at least with this physics question, you can answer it in two ways. You can either use the triangle or you can use algebraic reasoning. But the key point is you also have to have the assumptions about the conservation, total conservation, conservation of momentum before and after. Okay, so the sum of the two crashing, colliding out and bouncing off will be the same as the momentum at the start. Yeah, you could do the triangle way. Yeah, there are two ways you can do it. I've just done the algebraic way, but I'd suggest, because we've done it primarily in class using the triangle way with the vectors, I would potentially use that one. But the key is that's an isosceles triangle, not a right angle triangle. Right, calculate the speed. All right, let's do that. Yeah. Okay, so calculate the speed. Okay, so little diagram there. You'd have that, you'd have that, and that would be your total momentum. So momentum A, momentum B, and the tote. And that's your 20 degrees. Yep. Okay, so so the initial momentum will equal mv. Okay, and let's see what this. So the mass was 100, wasn't it? What's the question? Calculate the speed of rocks of A and B. Yep, so that'll be, why is it 100? That's a good question. Objects, oh, wait there. 100 kilometers are there. There you go. That's why. That's separation. Okay, cool. That's why. Okay. So it's 100 to start off with. Yeah, so 100 times 500. Yeah. Okay, so that equals 50,000 kilograms per meter per second. 50,000 kilograms meters per second. The final momentum is also going to equal that because you've got conservation of momentum. Okay. So therefore, momentum will be mv cos 20 degrees for one fragment will equal 200 times, 200 times, yep, v cos of 20. So also remember your calculators have to be on degrees, not radians. Otherwise you'll get the wrong answer. So the sum, there we go, of the two fragments, momentum in the x direction equals p. So therefore 2 times 200 v cos 20 degrees equals your 50,000. 50,000. Let's bring this down slightly. Oh, there's lots of room. Yay. 50,000. Therefore, just rearranging the equation, the velocity will equal 50. What's that? Yep. 50,000 divided by cos of 20 degrees times 2 times 200, which equals 133 meters per second to the minus 1. And if you look at the original values, you're probably looking at a sensible number in terms of its velocity. Okay, so about 133 meters per second. Okay. Cool. Oh, okay. So to get achieved for that section, it will be a calculation of initial momentum and recognition that momentum is conserved. Okay, so just saying it's conserved gives you an achieved as your assumption. The correct method, either the algebraic or the triangle method, which is that one there, the triangle method there. Okay, that again will get you a merit. Okay, and then the complete answer where you've got 133 meters per second will get you the excellence. And if you make a mistake and you have 2 there and you have 266 meters per second, that's still giving you a merit. So always attempt in these questions, try and get as much down, try and get as many marks as possible. Okay, so there's definitely going to be a question on two-dimensional momentum. I actually don't gamble, gambling's wrong, but if I did gamble, I'd put money on it. Right, so question 3, the pendulum in Mars, so I'm thinking SHM. Okay, so some space explorers on Mars want to check that their electronic timers are functioning correctly. They make a simple pendulum using a large rock with a mass of 2.3 kilograms. Doesn't gamble, that's right. Yeah. On Mars, the gravitational field strength, so wait there. So let's get through what we need. Okay, so we've got something to do with time. The mass is 2.3. Distance from center of mass of the rock is 1.83 meters. Gravitational field strength 3.72. So basically, it's just showing that the time period. So the time period of the pendulum is 4.41 seconds. Okay, so that's pretty much, again, looking at your formula sheet, looking at pendulums. So you just got to choose the right one for time period. There's only 2 equations. There's the one for the springs and one for pendulums. So this question, if there is a question on this in the exam, either will be a spring or a pendulum to illustrate SHM. Okay, so the one to use is time period equals the 2 pi, the square root of L over G. Okay, and you just plug in the numbers, 2 pi, the square root of the length, which is given as 1.83 meters in the question, divided by G, which is, because it's on Mars, 3.72. You plug in the numbers, and you should get an answer of 4.41 seconds. Okay, that's your achieved point there, just to show about choosing the right equation. Right, so they set the pendulum oscillating, okay, to release the pendulum bob 0.300 meters away from its rest position, and at the same moment, they start a timer. Okay, determine the position of the pendulum bob from its release point 2 seconds after it's released. Okay, so we've got 2 seconds. So there you go. And we've got an X position or a Y position. You may use a phasor diagram to help you with your answer. Okay. I guess you could. Okay, so phasor diagram. Well, first things first, because we're dealing with SHM and we're dealing with phasor diagrams, the first thing you've got to work out is your angular velocity. So omega equals 2 pi over t. We've already looked at that previously in question 1. So we plug in the numbers, and it's 2 pi over, what's our t? What's our t? Oh, yeah, that's first answer. 4.41 seconds roughly. Okay, so it's about 1.43 seconds minus 1. Okay, and theta from our equations will be omega t. Okay, so you plug that in. So t is 2 seconds from the question. So 1.43 times 2, which is 2.86 radians. Okay, that's your theta. We did not do it that way. There we go. There's your radians there. That's theta. Okay. And that's when you start using your, well, the way I do it is using the equations, which you're provided to. Y is theta omega t. So it's basically a rearrangement of a distance time. So the analogous would be distance equals velocity times time. Okay, so for analogous for linear momentum, so distance for an object undergoing SHM is the angle, okay, and omega is velocity and t is time. Okay, so that's why theta equals omega t. Okay, so it's analogous to linear velocity. Yeah, done. Yeah, it's fine. Okay, so where were we? Okay, so if we look at that, the equation that you'd choose is because we're starting at a release point. Okay, so it's not, okay, so the distance in the x direction will be, if you look at your equations, the amplitude, which is 0.3 here. Okay, so that's your A, 0.3 cos 2.86. Okay, because that's theta. That's it actually, yeah. So that would equal negative 2.88 meters. Okay, and in terms of reference, that's basically the distance in the x direction. Okay, so you use SOHCAHTOA if you want to use your reference circle to work out what x is. There we go. Or you can just use the trigonometric equations. So it's 2.88 meters. We're not quite there though, because the distance from the release point, okay, so if you go back to the question, the release point is actually 0.300 meters from the equilibrium. So to get that, it's an excellence point. It is. To get the excellence point, you have to add that on. Okay, so you've got 0.300 plus 0. Whatever, we've done something wrong. All done it wrong. It's not 2.88 meters. It's negative 0.288 meters. Otherwise, it's a crazy number. Okay, so plus 0.228. Okay, so it's only negative because it's just basically its position, whether it's going to be one side of the equilibrium point or the other. So it's basically 0.588 meters. Okay. Yeah, there we go. Let's get your excellence point. Yeah, so to get for that question achieved, it's either the correct angular velocity, or you're using the A cos omega t, okay, which is derived basically from your equations, which you get access to, okay, or you're using the phase diagram. If you have the correct X, that's what you achieve to get correct X. Correct process, but uses a sine instead of a cos. So even if you use sine instead of cos, you'll still get a merit. And then the correct total distance will get you the excellence. There we go. Okay, so we have part C then. The amplitude of the pendulum decreases. Okay, so it's gone now from 0.3 to 0.2. Explain why the period of the pendulum remains unchanged. So again, I just like using equations just to make things easier. So time period equation is 2 pi square root of L over G. So why does the, actually, what does that C? The amplitude, yeah. Okay, so as you can see from the equation, it's all about the length or the gravitational field strength, nothing about the amplitude. It's not dependent on amplitude, so you don't have to worry about it. Okay, so either it travels less distance, speed decreases proportionally, acceleration, or you link it, as I've just done, to the correct equation. T is actually independent of the amplitude. There we go. So I always like using equations. Just makes things easier. That's what we have them for, to make things hopefully easier as physicists. Okay, so length stays the same, G stays the same, amplitude might change, but who cares? It's not in the equation. And the last part of that question, nearly finished. Calculate the total energy lost when the amplitude decreases from, so it's going to be decreases from 0.3 to 0.2 meters, and begin your answer by calculating the max velocity of the bob for the initial and final, amplitude. Okay, so energy, as we know from even level 1 physics, is half mv squared. Okay, our max velocity is going to be the amplitude omega. Okay, so that's basically the distance and time. Okay, so a omega. So we might actually calculate that. So the amplitude from our previous questions is 0.3, and the omega right from the start is 1.43. Okay, so our max velocity is 0.429. Okay, cool. So if we just plug in the numbers, so energy equals half. How come there's no cos omega for the max? We'll think about what omega t is. Yeah. So it's the max. So that's all down to when the velocity is maximum. So that's actually at equilibrium. So there's no theta. So it's going to be going straight through the center. That's when the maximum velocity is. So at the top of the, maybe we'll draw it on here. So at the top of your, actually no, it's a pendulum, isn't it? So at the top, it's going to be a minimum velocity, and it's going to be the maximum velocity when it's going through the equilibrium point. Okay, that's why. Yeah, there we go. Right, so half mv squared. So we just plug in the numbers. So the mass is times 2.3 times 0.429 squared, which equals 0.212 joules. Okay. And that will get you an achieved. And then the max velocity is again, so if we've changed it 0.2. It's now changed from 0.3 to 0.2 times 1.43, which equals, bring that down a bit, 0.286 meters per second to the minus 1. Again, we do the energy calculation. That will equal half. Yep. The mass, 2.3, isn't it? 2.3 times now 0.286 meters per second, which equals 0.094 joules. So the energy lost, change in energy, will be 2.12, or 212, sorry, minus 0.094, which equals 0.118 joules. And that's where you get your merit from. Yeah, boom. I think that's it, isn't it? So what's the question ask? Oh, go up again. Calculate the total energy lost. Yep, there we go. 0.118 joules. There we go. So that is the wonderful world of mechanics. So in terms of mechanics, some little tips and hints. There's a lot more work for merit. Well, I guess for that question, you're only doing 2 calculations. Most of the excellence questions now, it's got E7 and E8. So E7 would be a calculation one, and E8, which is new for this year, are more the written explanations, but because we're physicists, you can use equations for that as well. So you actually get 2 chances of excellence this year. There's an E7 option and an E8 option. So actually lucky in that regard. Yeah. Right, so in terms of the standard itself, some little things to be wary of. Okay. So in terms of rotational motion, it's important to remember those conditions, making those assumptions. Okay. In terms of conservation of momentum and the application of force to create the torque. Okay. And be clear that you know the difference between rotational motion and circular motion. Okay, so that's quite important as well. Okay. Yeah. So also, generally from last year, candidates who demonstrated practiced algebraic skills and understood the concepts did quite well. Okay, so understanding the concept behind the equation, not just writing the equations. So rotational motion is essentially you're looking at the entire object rotating, whereas circular motion is that the okay, maybe I'll write it down here. Can I do that? Spare diagrams. Oh, okay. So circular motion is we're actually looking at the object in the circle. Okay, whereas rotational motion, we're looking at the entire object rotating. Yeah, just to clarify that point. Okay, so orbits are an example of circular motion, whereas a bowling ball going down a hill is an example of rotational motion. Yeah. So this year, it's important that candidates need to demonstrate their working for showing equations, and that includes choosing the right formula, substituting appropriate units, and coming up with the required answer. Okay? And so it's about also being able to apply the physics knowledge to the question, E8, essentially. Yeah, so that's the things orbiting around an object is circular motion, whereas the whole thing is rotating, then that's going to be more rotational motion. Okay? So in terms of those students that were awarded achievement, you had to completely show your working. Okay, that's your show questions. So being able to calculate the position of the center of mass, being able to use the law of the universal law of gravitation, conservation of linear momentum has to be mentioned. Okay, explaining parts of the conservation of angular momentum. So in terms of not achieving, students that got not achieved tended to not completely show working in their showed questions. Okay, so you have to show the working, obviously. Did not calculate the position of center of masses, did not incorporate the universal law of rotation, and did not state the ideas around conservation of momentum. Okay, they did not use equations to show the relationship. So that's the example with your excellence questions. If you write down the equation and then work from the equation, that's where you're starting to work to be able to explain things. Did not understand the role played by angles between force and distance in terms of torque. Yeah, so that's kind of not being able to differentiate between mass and weight. If you're aiming for merit, then it's about, it's the calculations, your two-step calculations. And excellence, you have to really understand the concepts behind it. Yeah. Okay, so for example, the state of the conservation of linear momentum, calculating initial time momentum of the system. So you really have to know your stuff to get your excellence. There we go. So that's the wonderful world of mechanics. Okay, so obviously we have two papers to look at. So the next one we're going to look at, let's see if it actually works if I just change tabs. Just checking if that works. Who knows? Doesn't. Oh, did it work? Did it work? No, it doesn't. Nah. I have to be able to, okay, so stop sharing. Okay, and I'll just close that. Yep, that's fine. Yep, so welcome back. I'm now just going to be sharing the next exam. Right, so present, share screen. There we go, level 3 physics, electronics. Cool. Okay, Yo sir, can you let us know of the equations that we must memorize for mechanics? No, because I don't know what the equation, what questions will be asked. I think it's more the principles, the idea of conservation of angular momentum, conservation of linear momentum, and also practicing the processes within like the exams tomorrow. But the idea of being able to use SOHCAHTOA, for example, for the level 3 collisions. Yeah. Most basically the equations that you have on your exam sheet should be sufficient. But I would suggest maybe going over the level 2 physics equations because they should be known now. They don't necessarily have to be in the exam. Yeah. There we go. Anyway, so on to demonstrating an understanding of electrical systems. Okay, so there'll definitely be an AC. What about the ones like I is? Oh, yeah. So the idea that the inertia is equal to the sum of the mass times the radius squared. Chances are you might actually get an object, which may not just be a normal sphere. It could be a pipe or a hollow sphere. And in that case, you would be given the equation for it. Because the I equals the sum of the mass times the radius squared is a generic equation based on the fact that the center of the mass is evenly distributed in the object, and that may not be the case. And if that is not the case, then you will be given that equation in the question. Yeah. Okay. So moving on, AC circuits. There'll definitely be a question on AC circuits tomorrow. I can bank on it. So let's look at George's wonderful investigation of AC circuits. So George is investigating AC circuits. He connects a 50.0 microfarad capacitor in series with a 36 ohm resistor and a 25.0 VRMS 50 hertz AC supply, as shown in this glorious diagram. So show the reactance of the capacitor is 58.9 ohms. Okay, so that should be quite straightforward because that should be, or will be, on your formula sheet. Okay, so it's basically, oh, yeah, was it not? Okay, but actually do the drawing thing. There we go. Okay, so XC equals 1 over 2 pi FC. Okay, so plug in the numbers. So 2 pi, the frequency is given. Yep, it is. Times 50 times the capacitance, which is 50 times 10 to the negative 6. So if you plug in those numbers, you get 58.95 ohms, because reactance is kind of the equivalent of resistance in a AC circuit. Okay. Right, next, oh wait, there, gone too far. Okay, so B, calculate the circuit current. Okay, so in terms of the circuit current, so this is where you're using your trigonometry. Okay, so that you're going to be using Z equals R squared, actually the square root of, really, square root of R squared plus XC squared. Okay, so if you plug in the numbers, you get the square root of 36.0 squared plus 58.9 squared, which is 69.1 ohms. Okay, so that gets you a impedance, but V equals IZ, okay, which is analogous to V equals IR for a DC circuit. Okay, so you just have to rearrange it. So therefore, what are we trying to find out? The current. So current will equal V over Z. I think we've given the voltage at the start, haven't we? 25. Yep. Okay, so that's going to be 25 divided by Z, 69.1. which equals 0.362 amps. Yes, you probably, yeah, you do. But that all comes with the AC, with the idea of the Eli the Iceman. I'm sure you've, yeah, so yeah, phasor diagram, correct. It's the phasor diagram stuff, which I think really comes in later as well. So yes, that is correct. It is indeed the phasor diagrams. Eli the Iceman. Yes. Oh, in fact, there we go. Phasor diagram. Boom. Okay. So calculate the phase difference when the supply voltage and the circuit current for the circuit shown on page 2 state which one leads. That's your Eli the Iceman. Ice. Draw the phasor diagram in the space below. Okay, so you basically got that going there. Oh, regulation. Isn't it usually XI and XC, R and XC? Yeah, well, it depends on the circuit. So in this particular case, because we have a capacitor only in our circuit, we don't have to worry about XL. There's no inductor. So we're all good. Okay. So yeah, that's our XC. That's our XR. Well, actually, no, that's just R really. There's no XR because it's just a resistor. Okay, and then we just use that, yeah. So it depends if we're an LCR circuit or yeah, what they've actually got in terms of the construction. They might have had a inductor in there, which means the inductor would have been, so rather than having that, you would have had it 180 degrees out of phase. Yeah, that's what Eli means. So basically the voltage leads the current, or the current in a inductor, whereas the current leads the voltage in a capacitor. That's what Eli the Ice means. Yeah, so if it would have been an inductor, then that would have been there instead. But it's not in this case, it's down the other way. But it's possible that you could get a LCR, an LCR circuit, which means then you have to find, I'm not sure what the rest of the question could possibly be, but you'd have to find the overall, which means you're going to subtract the XC from the XL to get X total, which is a little bit more complicated. Yeah. Anyway, calculate the phase difference. That's what we're trying to do. Okay. So current is in phase with the resistor voltage. Yep, got that. And therefore, theta, that's what we want to find. Theta here will be equal to the inverse tan of 58.9 over 36, which equals 58.6 degrees. There we go. So the current leads the supply voltage by 58.6 degrees. So it's possible what they could do is they could have a question on capacitors or inductors completely, or they could have one on an LCR circuit, or they could start off with a capacitor and they might add an inductor, and you have to calculate the whole circuit in that regard, the LCR. That's where the phase diagrams come in. Oh, there we go. Explain, there we go, suitable inductor. We've already mentioned it, so we've got capacitors to start off with. Explain how the addition of a suitable inductor to the resistor capacitor circuit of the AC supply can make the circuit resonate. Okay, so resonance, that's always nice. Begin your answer by explaining what resonance is. Okay, so let's be careful with this. Okay, so basically resonance is when current is a maximum. Okay, and that's when impedance is a minimum. And this happens when XC equals XL. Okay, and when Z equals R, and the supply voltage equals the resistance voltage. Because these guys cancel out, then yeah, it's when the voltage. Yeah, we love resonance, we all do. Because you've also got resonance possibly in mechanics as well as possible question. Okay, so an inductor whose resonance is the same as that a capacitor should be added into the circuit, because that way XL will equal XC. There we go. So if you have all those points, that's your excellence point. Oh yeah, so basically add a inductor with same inductant, oh not same inductance, what's the word? Reactance, isn't it? As capacitor. Well, yeah, that's exactly the same thing, isn't it, really? Yeah, it's X, yeah, the reactance of the capacitor equals the reactance of the inductor. I've just put it in words. Yeah, fine. Right, so that's actually, I thought for 2022, that was not too bad for AC circuits, to be honest. Especially when we didn't really discuss LCR. So LCR would be the, so going to that question. So to get an achieved, basically stating that of one condition for resonance, and to get a merit, two conditions, and three, the whole bang. So basically you're saying that the current's a maximum because the impedance is a minimum, and if you add an inductor with the same reactance as the capacitor, you get resonance, and that's your excellence. 3 points. That's pretty straightforward, I thought. Right, so then we have question 2. So now it's David. He's investigating inductors and magnets. He uses a 1.6 Henry inductor, or 22 ohm inductor. Yeah, okay, there we go. and connects to 12 volts to the power supply. The inductor can be considered as the pure inductor in a series with a resistor, as shown in the diagram below. So calculate, okay, this is the achieve point, calculate the circuit current after 2 time constants. Oh, once the switch is closed and the current begins to flow. That's a little bit different. Okay, I can do that. Imax will be the supply voltage divided by the resistance. This is the merit question to start off with, quite bold. Okay, so it's 12 divided by the resistance, which you're given in the question. So we have a maximum current of 0.545 amps. Okay, so that's your first achieve point. Okay. Now is it going down, isn't it? Yeah, so basically 0.67 will actually be of its value. One, is it one? No, 0.37. Let's double check that with the calculator. 0.545 times 0.37. No, it's not. It's 0.67. 0.545 times 0.67 roughly. Huh. Yeah, okay. How did they get that? That's interesting. It's always embarrassing when this happens. Oh, okay. So it's how much it loses. Yeah. Okay. Yep. Okay. So basically, it's losing 67% each time. So it would be 0.5545 times 0.67. Oops. That's right. 0.67. 0.545 times 0.67. Right, so it's so on the first decay it loses 0.365. Yep, okay. Times 0.67. Then it's 0.2. 0.244. Right, so if we subtract those away, it should work. Okay, I'll do it a different way. Okay, so the current will equal the Imax, and because it's a decay curve, natural logarithmic decay curve, it'll just be 1 e to the minus 2. Okay, so minus 2 because I'm trying to think that, but the way I did it, it's more accurate if you use it just a logarithmic decay curve, natural logarithmic decay curve. So hopefully that works. So Imax is going to be 0.545. Then you multiply that 1 e to the minus 2 because it's 2 decays. And that should give you an answer of 0.471. Oops. There's 2 time constants. Oh, 63%, isn't it? Yeah. So basically, it cuts by 63% the first time, and then 63% of that original value. So whatever that is. So 0.545 times 0.63. Yeah. That's how much is lost. And then 0.63 again. It just keeps on decaying like that. So you should get an answer of 0.471 amps of the original. Yeah. Okay, so next question. State the voltage. Okay, back to the equation. State the voltage across the pure inductor and voltage across the resistor once the current is steady. So the voltage across the pure inductor, it's easy. That's basically going to be 0 volts, okay, once the currents are steady, because there's no change in flux. Okay. And the voltage across the resistor, therefore, well, you've got started up with 12 volts, so it must be 12 volts, because the sum of the voltages in the circuit has to equal 12. So if the inductor is 0, then I don't have to do a calculation for that. Yeah, so if it's 0 volts across the inductor, then it must be 12. Hey, we're multiplying it by 0.63. Current after 2 time constants. It's losing 37% each time. Maybe they got the calculation wrong in the answers. 0.545 times 0.63. Okay, we'll try it this way. What's that? Right, so e to the negative 2. Let's see. Shift with e. Oh, where is e in the damn calculator? I should know that. Oh, they got e to the negative 2. 1 minus answer. Times 0.545. Yep, 0.471. But I wouldn't give that. I would say that's what's lost. I would say they've stuffed up. That's the current that has been lost. So it's 0.545 minus 0.471. Doesn't even make sense. 0.55 times 0.37 is 0.37. Yeah. So the voltage that would have been lost, so that's changing current. Okay, so that means that it's 0.07 amps after 2 time constraints. So okay, 37%, 37%. That makes a lot more sense. Right. That's how much lost. Okay, so once the current has reached a steady value, the switch is opened and the current falls to 0 at 2.5 times 10 to the negative seconds. Calculate the size of the average induced voltage and then also state the direction. Okay, so this is straight from your equations. So this is going to the back EMF one. No, I'm going to use the equation we've been using. Okay, so E equals L change in current over time. Okay, so if we just plug in the numbers, the voltage, not just the EMF, equals 1.6 times we've got a current first, don't we? Yep, okay, so we won't do that yet. Got to work out the current first. So current equal, actually got the current in the previous example. What am I even doing? The current's already there, 0.545. Yeah, okay, right, so back to that. So the current is, that's equals 1.6 times 0.545, which we've got from the previous example, and the time period is 2.5 times 10 to the negative 2, straight from the question. So that equals 34.9 volts. That's the induced in the inductor. State the direction. So since the induced voltage opposes the changing current, it will try to prevent the current from decreasing. So it will be the same direction as the source voltage. There we go. Okay. And the reason why is because it's the induced voltage opposes the change in current, delta I. This is always actually a negative value. Okay, so that means the change in current is going in opposite direction. So that means that the EMF will be in the same direction as the supply voltage, which is what we get with Eli the Iceman. Yeah, it justifies it. Okay, so in terms of that question, to get the correct value of the induced voltage, that will get you an achieved. And if you have the correct value and the correct direction, then that gives you your your merit point. That's only a merit. Okay. So then we have a 22 ohm resistor. It's replaced with they say double the resistance. Switch is all closed. So yeah, these questions, these open close questions, again, I can probably bet my house if I actually had a house, that these questions will be in there. Okay, so Lenz's law. This is all about Lenz's law. These kind of questions will be in the exam. Okay. So the time constant and the energy stored by the inductor once the current is steady. Okay. Okay, so going to increase the resistance. Okay, there we go. Okay. Okay, so because current equals V over R, increase the resistance, then it's going to size of maximum current. That's going to go, yep, that's going to halve, it's going to decrease. Okay, so you've doubled the resistance, you've halved the current. Okay, so 2R just means half I. Okay. So time constant equals L over R. So again, we've doubled the time constant. So, sorry, not doubled the time constant, doubled the resistance. So we're going to have our time constant as well. Okay, so that's going to be half because you've got 2R again. Okay. And the potential energy in the system will equal half Li squared. So we've halved the current. So that means it's going to decrease it by a quarter. Okay, so I squared, it's half I squared, that's going to be a quarter EP. There we go. So 1 point of those three, so there's your first point, there's your second point. Oh, second point. I'll move that up slightly. And there's your third point. So yeah, 1 point, that gets you achieved. 2 points gets you your merit. And 3 points gets your excellence. Okay, again, the beauty of using the equations. Okay, no questions. Awesome. Oh, look at that. Oh, this question was a lot about AC. Okay. So with question 1 was about inductors and it's in DC, sorry. So yeah. So inductors in AC, this is capacitors in DC, important distinction. But yeah, so now we have Anne, she's doing her thing. What's she doing? She's carrying out an experiment, just like the other two have done. This time using parallel metal plates to investigate capacitors. She takes a pair of metal plates, so they've got an area, and connects them to a 9 volt, this time DC supply. So we don't have to worry about changes in volume and things. And they're separated by this distance. Oh, I know what we've got. It might be an equation. Show the capacitance. Okay, so again, we've given all these values. We've got epsilon, a relative epsilon of 1, makes the math a little bit easier. Distance, and a voltage, but I think the voltage is necessarily important. So the equation we'll be using is epsilon naught, epsilon relative, area divided by the distance, which should all be there. So that's a constant, which you have in your exams sheet. Relative is 1. That's easy. And 0.16. And we just divide that by the distance. Yeah, because the area is up here, that makes sense. And the distance is 1 times 10 to negative 3. We E naught. So E naught is the relative permittivity of free space. That value will be given to you in the exam. So you don't have to memorize it. It's there. So basically, it's the amount of charge that can move in vacuum, really. Okay, so if we plug those numbers in, then we get 1.42 times 10 to the negative 9 farads. That's your achieve point. Shimposh. Oh, wait. And ER is the material between. Yeah, that's correct. So in this particular case, it's air. So rather than having a vacuum, they put air between the plates. And that's relative to the permittivity of free space. Yeah. So actually, it's just permittivity of free space divided by the permittivity of free space, which is 1. Because air vacuum is actually very similar in terms of its conductance, surprisingly. Yeah. Right. So BI, calculate the energy stored in the capacitor once it is fully charged. So again, you're looking at the equations you have on your, nice A. Yes, so easy A. Okay, so that's, what are we doing? Describe energy stored. Okay, so energy is going to be equal to half CV squared. Actually, let's move that slightly so we can see the values. We got CV squared. So let's plug in the numbers. It's a part B, that's why it's a merit. Half the capacitance, which was 1.42 times 10 to the negative 9. Yep, that's from part A. Times the voltage squared, which is 144, no, 9 squared, sorry, 9.0 squared. Plug in the numbers, and you get 5.75 times 10 to the negative 8 joules. Okay, so that's going to be your achieve point for that first part of the question. And then the merit point will be describing the effect. Okay, so describe the effect on the energy stored in the capacitor with a sheet of mica, which has a relative permittivity this time of 7. So it's a lot harder for the electricity or the charges to move in the mica as opposed to a vacuum or air. It's introduced between the capacitor plates. Okay. So because of that, okay, so you've increased the relative permittivity to 7. That means charge will be stored on one side of the plate, on plates. So therefore, the capacitance also increases by 7 times. So from the equation, if you increase that 7, then the energy will also increase by 7. There we go, and that's your merit. Woo. Whoop, whoop. Okay, part C. So then Anne disconnects the plates. Okay, so there's no more current or voltage or anything flowing. Okay, they're isolated. Then she pulls the plates apart. Oh, dangerous, Anne. Explain what would happen to the charge on the plates and the voltage across the plates. Okay, so in terms of the charge, Q, there's no voltage, so there's nothing pushing the charge. So the charges on each of the plates will stay the same. No problem. Okay. But because, if you look at this, the capacitance relies on the distance. Okay. Obviously, that distance is greatly increased, and Anne's gone mental and pulled the plates together, pulled the plates apart. So therefore, because D's increased, then the capacitance also increases. Okay. In terms of the voltage, though, remember Q equals, not Q, sorry, that's not right. C equals Q over V. So if we've gone and increased the capacitance and Q's all good, it stays the same, then the voltage also has to decrease. So C equals Q over V. Oh, yeah. Oh, wait there. What am I doing? No, it's an inverse relationship, isn't it? I know, done wrong. Yeah, okay. So C and D are inverse. Brain fade late at night. Well, late at night, but still. Right. So distance. Yeah. So distance increases. The capacitance goes down. Opposite. Sorry. It's an inverse relationship. Brain fade. Okay. So that means that this is not right. Capacitance goes down. And if capacitance goes down, then it's in relationship between voltage and capacitance, so the voltage goes up. There we go. That makes a lot more sense. Okay, so get one of those points correct, that's your achieved, and get two of those points correct, and that's your merit. There we go. Yeah, so why does C go down? So yes, C, so if you look at the equation that we've already got for part A, you can see that the capacitance is proportional. What? Okay, yeah. Okay, so let's go all through that again. Okay, let's do that again. Okay, great. Okay, so Anne disconnects the plates from 7 volts. So the plates are electrically isolated. Okay, then pulls the parts apart the plates. So the distance between the plates increases. Okay, so what happens with the charge on the plates? Well, because there's no voltage pushing any of the charges anywhere, the charges on the plates stay exactly where they are. So the charge on the plates is the same. There's nothing moving anywhere. Okay, so Q stays the same. Right. Then ask, well, what happens to the voltage across the plates? We've already mentioned that the distance between the plates increases. So if you look at the equation here, the capacitance equals epsilon naught times the relative permittivity divided by the area, multiplied by the area divided by the distance. Okay, so as the distance between the plates increases, okay, it's an inverse relationship. So as the distance increases between the plates, the capacitance goes down. Okay, and then because capacitance equals the charge divided by the voltage, okay, as the capacitance goes down, the charge stays the same. The voltage, because it's an inverse relationship, means it goes up. Yeah. Okay. Comprende. Bueno. Okay. Right. So last question. And then experiments with connecting different capacitors in series and parallel across the 12-volt supply, as shown in the diagram below, or complex. Calculate the voltage across the 4.7 times 10 to the 2 microfarad capacitor. And then the first thing you have to do, it says, well, you've got to start to calculate the total capacitance. So the funny thing with capacitance in parallel compared to capacitance in series, okay, so capacitors in parallel the more you add, the more the capacitance goes up, whereas in series, the more you add, the capacitance goes down. It's the opposite of resistors. Okay, so let's do this. So the total capacitance equals 1 over the total capacitance, because that's going to equal 1 over the 470. Well, in a question like this, would Q remain constant? Yes. Well, yeah, because the charge going into the battery has to equal the charge going out. So yes, charge overall for the system would. Yeah. That's right. Right, so where were we? 470 microfarads plus 1 over 800 microfarads. Okay. Where I get 800, it's the one. Okay, so if you do the calculations, the total capacitance equals 296 microfarads. Okay, that's the first part of the question there done. Okay, so you already mentioned the charge. It's like you've looked at the answers potentially. Okay, so the total charge, okay, which we'll call very imaginatively QT, equals the total capacitance times the voltage. Yeah, so that's what we've already looked at there actually. So look at that. C equals Q over V. Let's rearrange the equation. And we get the total charge equals the total capacitance times the voltage. Okay. And if we go down, there we go. What are we doing? So that will equal 296 times 10 to the negative 6 times 12. Which equals 3.55 times 10 to the negative 3 coulombs. And therefore, the voltage across the 470 capacitor will equal, is there any questions? No. Equal Q over C, which equals 3.55 times 10 to the negative 3, going down slightly, divided by the total capacitance, well, for this particular capacitor anyway, times 10 to the negative 6, which equals 7.56 volts. There we go. So in order to get an achieve for that, calculate the total capacitance or calculate the total charge, but you make an error in the capacitance. If you get the total charge or there's one error in your calculation, that's your merit. Your excellence is you get 7.56 volts. But the only slight change this year will be there'll be probably an explain question in these sections, which is where you get your E8 answers from. There we go. So that is electrical systems. Now, let's look at the commentary. Yep, I'll just look at the commentary for last year. Okay, to give a little bit more in the way of hints for tomorrow. Okay, so looking at electrical systems, I'll look at the ones where they got not achieved. Okay. Does this mean that even if I get it wrong? Yes, that's right. So even if you've got an error in the calculation, you would potentially get a merit. Because that's the key, basically. Write out as much as you can get into your equations, and you might be able to get a merit, even though you can get error carried forward. Right. So candidates who were not awarded achieved in this standard, yeah, that's on. Okay. They did not respond to the question. Okay, left question paper blank. That's obvious. If the key, I guess, which I've done for the explain questions, understanding the relationship between the variables and how altering one variable, like say doubling it, affects the other variable. Okay. Confuse capacitance with inductance. Okay, that was a big thing. Did not use phasor diagrams or trigonometry. Okay, and that's, I think, also the same for mechanics, really. Did not recognize the need for phasor addition. Okay, so that's basically your trigonometry and having the hypotenuse as your addition. Did not express the changes in relationships. Did not have nothing of resonance. So I think there will definitely be a question in resonance for this particular unit. Did not understand how inductors and DC circuits work. So that's the idea of Lenz's law. So the one thing I would suggest for tonight after watching this is go over your notes around Lenz's law, because I'm pretty sure there'll be questions. Well, I'm going to find out tomorrow. That is for sure when I look at the papers. Yeah, so that's pretty much it for electronics. Yep. What's Lenz's law? So I'll stop sharing. So basically, Lenz's law is the idea. Yeah, so basically, Lenz's law is that you're going to create a current or a voltage in opposition to the supply voltage. Okay, we'll talk about voltage essentially. Okay, so in an inductor, what you're doing is that when you're creating a electrical field, then you're going to create a magnetic field. That magnetic field is going to create another voltage, a back EMF, which is going to resist the change in current. That's essentially Lenz's law. So it's like making the circuit equal zero. Yeah, so the big examples, so the idea would be, I'd suggest looking at your notes around inductors when the circuit is open, and then looking at what happens when you close that circuit. Okay, so essentially what happens when you close it, you usually get a spark. No, that's internal resistance. Yeah. So the equation you're looking at is the L delta I over T. That's your back EMF equation. Yeah. Okay, right. So yeah, so thanks for joining and all the best for tomorrow. I leave you with the word of Sun Tzu. The battle should be fought before it is won. Okay. Hare Ra.